Hello everyone. Today we will discuss building production RAG systems. In this section, we compare systems with and without retrieval augmented generation. With RAG, a user query goes through a knowledge retrieval step before reaching the LLM, resulting in a grounded response. Without RAG, the user query goes directly to the LLM, which generates a response based only on its training data. Retrieval augmented generation allows large language models to use external knowledge sources instead of relying only on training data. Without RAG, a model can only answer from what it learned during training, which may be outdated, incomplete, or entirely absent for domain-specific topics. With RAG, the model retrieves relevant documents at query time and reasons over real, current data to produce grounded responses. Why RAG is needed with RAG, a user question is followed by knowledge retrieval, then passed to the LLM with context, producing an accurate answer. Without RAG, the question goes directly to the LLM, which may result in hallucination. RAG systems allow AI to use up-to-date enterprise data. LLMs have a training cutoff and cannot know about events or data created after that date. Enterprise knowledge such as internal policies, product documentation, and customer data is never part of the training set. RAG solves both problems by retrieving the right information at query time, making the model's knowledge current and domain-specific without retraining. Basic RAG architecture. The RAG pipeline starts with a user query. This query is converted into an embedding vector, which is used for vector search. Relevant documents are retrieved and passed to the LLM for reasoning, producing the final response. The pipeline retrieves relevant information and injects it into the model prompt. The top results are assembled into a context block and included with the query. The LLM then reasons over this context to produce a grounded and accurate response. Embeddings. Embeddings convert text into numerical vectors that capture semantic meaning. Documents are converted into vectors at index time, and queries are converted into vectors at search time. Similar concepts produce vectors that are close together in high-dimensional space, regardless of the exact wording. This enables semantic search, where the system finds documents based on meaning rather than keywords. Vector similarity, search vector. Similarity search retrieves documents based on semantic similarity. The query vector is compared with stored document vectors using cosine similarity, which measures the angle between vectors. Documents closest to the query vector are considered most relevant, and the top results are returned as context for the LLM. YPG vector enables vector search inside PostgreSQL. It removes the need for a separate vector database. By adding vector columns and similarity operators, PG vector allows relational data, metadata filtering, and vector search to run in a single SQL query. This simplifies architecture and reduces operational overhead. Amazon Bedrock for RAG. Amazon Bedrock provides managed foundation models with simple API integration. It allows developers to build AI applications without managing infrastructure. A single API call invokes the model with a structured prompt. Bedrock handles scaling, security, and monitoring automatically. Claude for retrieval systems. Claude is well suited for RAG systems due to its strong reasoning capabilities and large context window. It can process large amounts of retrieved context and synthesize information across multiple documents. This makes it effective for enterprise use cases where accuracy and safety are critical. Knowledge base architecture. Documents must be ingested and transformed into vector representations. The process involves splitting documents into chunks, generating embeddings, and storing them with metadata. Metadata such as tenant ID, source, and timestamp enables filtering and multi-tenant isolation during retrieval. Chunking strategy. Documents are split into chunks of fixed size, typically 512 tokens, with an overlap of 64 tokens. This ensures that context is preserved across boundaries. Small chunks may lose context, while large chunks reduce retrieval precision. Overlap helps prevent loss of information between chunks. Embedding pipeline. The embedding pipeline processes raw documents by cleaning and normalizing text, splitting it into chunks, generating embeddings, and storing them. Each chunk is converted into a vector and stored along with metadata. This pipeline runs during ingestion and whenever documents are updated. Vector similarity query. Vector queries retrieve relevant chunks using cosine similarity. Metadata filters ensure tenant isolation. The system returns the top K most similar results, which are used as context for the RAG pipeline. Prompt construction for RAG. The prompt consists of a system instruction, retrieved context, and the user query. The system prompt instructs the model to answer only using the provided context. The context is included before the query to ensure the model prioritizes it during reasoning. Context assembly. Context assembly selects the most relevant chunks based on similarity. Duplicate content is removed and a token limit is enforced. Chunks are added until the token budget is reached, ensuring the prompt stays within the model's context window. Scaling RAG systems. Scaling techniques include semantic caching, parallel retrieval, and efficient indexing. Semantic caching stores previous query results. The HNSW index enables fast similarity search even for large datasets. Parallel processing improves performance under high traffic. Monitoring RAG systems. Monitoring tracks query latency, token usage, retrieval accuracy, and error rates. Latency is measured across retrieval and inference. Token usage affects cost. Retrieval accuracy ensures quality, and error monitoring enables quick issue resolution. Security and governance. Security is enforced through IAM policies, tenant filtering, and access control. Each query includes tenant-based filtering to prevent data leakage. Access control determines which users can access specific data, and all activity is logged for auditing. Production RAG architecture. The production architecture includes a front-end, API gateway, and back-end orchestration. The front-end handles user interaction. API gateway manages routing and authentication. Lambda runs the RAG pipeline, including embedding, retrieval, context assembly, and model invocation. Data is stored in S3 and RDS, while PG Vector handles vector retrieval. CloudWatch monitors the entire system. The architecture is serverless and scales automatically without infrastructure management. Thank you.